Welcome to video lecture 5G. I hope that everyone is doing well today. In the last lecture, I defined the cyclic burst error correcting capability of a code, and we established lower and upper bounds on this capability. In this lecture, I'll present the error trapping algorithm for correcting burst errors. We'll see that the algorithm is quite simple and is well suited for hardware implementations. I'll also present the technique of interleaving, which is used to increase the cyclic burst error correcting capability of a code. Let C be an NK cyclic code over F with canonical generator G of X. And suppose that C has cyclic burst error correcting capability T. We proved in the last lecture that T is at most n minus k. Recall also that we had this nice PCM for C in standard form, where the columns of the matrix H are the successive powers of X modulo G of X. Also, the syndrome of a vector R with respect to this PCM is a remainder upon dividing R of X by G of X. Here's the main idea behind the decoding algorithm. We're only interested in properly handling error vectors that are cyclic burst errors of length at most t. So suppose that the error vector E is indeed a cyclic burst of length at most t. So E might look like this vector, where all the non-zero components are within the first n minus k coordinate positions. Or perhaps E looks like this vector, where not all the non-zero entries are in the first n minus k coordinate positions. In the second case, some cyclic shift of E, let's say E shifted I coordinate positions to the right, has all the non-zero entries in the first t coordinate positions. Remember that t is at most n minus k. The syndrome Si of the shifted vector Ei is obtained by multiplying the first n minus k coordinate positions of Ei with the identity matrix and the last k coordinate positions, which are all 0, with the matrix minus R transpose. And so Si is equal to the first n minus k coordinate positions of Ei. Si might look like this, or it might look like this. I emphasized that this Si is a non-cyclic burst of length at most t. Now the vector x, which has Si in its first n minus k coordinate positions and zeros elsewhere, has syndrome Si. And so x has the same syndrome as Ei. This vector x is a cyclic burst of length at most t. And hence, since a coset of C can have at most one cyclic burst vector of length at most t, it follows that Ei must equal x. In other words, the shifted error vector Ei is Si, which is a vector of length n minus k, followed by a vector of k zeros. Once we learn Ei, we can recover E by shifting Ei n minus I positions to the right. So our decoding algorithm will compute syndromes of cyclic shifts of E until the syndrome is a non-cyclic burst of length at most t. When such a syndrome Si is encountered, we know that the shifted error vector looks like this, and we can obtain the error vector from this expression. So the question then is, how do we compute the SIs? Namely the syndromes of the cyclic shifts of the unknown error vector E. It turns out that computing the SIs is relatively simple. Suppose that C is a transmitted code word and the error vector is E. So R equals C plus E. Multiplying this equation by xi and rearranging gives us xi times R minus xi times E equals xi times c. Now c is a cyclic code, so xic, which is a cyclic shift of c, is also a code word. And so this equation tells us that xir and xie have the same syndrome. So we can compute syndromes of cyclic shifts of E by computing syndromes of cyclic shifts of the received vector, which we know. Here then is the error-trapping decoding algorithm for cyclic burst error-correcting codes. Let R be the received word. We'll denote by SI the syndrome of the ith cyclic shift of R. So now, for I from 0 to n minus 1, we'll compute SI. If SI has non-cyclic burst length at most t, then we'll let E of x be the polynomial you get by shifting this vector n minus I positions to the right. And we'll decode R to R minus E and stop. If no such syndrome SI is found, then we reject R and conclude that error correction is not possible. Let me justify the correctness of this decoding algorithm. Suppose that the error vector is in fact a cyclic burst error of length at most t. I'm making this assumption because I don't care what the decoding algorithm does if the error vector is not a cyclic burst of length at most t. So in the event that the error vector is a cyclic burst error of length at most t, we saw in the previous slide that some cyclic shift of E, let's say EI, will have its non-zero entries in its first n minus k coordinate positions. And in that event, the syndrome of EI is a non-cyclic burst of length at most t. When this event occurs, we know that the vector SI, 0 has syndrome SI. And it's a cyclic burst of length at most t. So, since C is a cyclic burst error-correcting code, this vector must be a cyclic shift of the error vector E. And therefore, the vector E is the vector EI shifted n minus I positions to the right. This decoding algorithm is called error trapping because in the algorithm, we repeatedly cyclically shift the unknown error vector until all its non-zero entries are trapped in the first n minus k coordinate positions. Lastly, let me note that the algorithm is especially well suited for hardware implementation. And that's because the operations involved in the algorithm are computing the first syndrome S0 of the vector R, which we saw is a polynomial division which is easy to do in hardware, especially if C is a binary code. And secondly, all subsequent syndromes S1, S2, and S3 can be easily obtained from the first syndrome S0. Let's do an example of error trapping. Recall that the 59 binary cyclic code with canonical generator given by this degree 6 polynomial is a 3 cyclic burst error correcting code. So t equals 3. Let's decode the received vector R, which has length 15, using error trapping. So we begin by computing the syndrome of R by dividing R of x by g of x. The remainder is S of x, which has vector representation 110011. We saw this calculation in the previous lecture. We then compute syndromes of cyclic shifts of R. Recall that we can do this by shifting the previous syndrome one position to the right. And if the rightmost bit is a1, then we add the vector g of x and delete the last 0 to get a vector of length 6. So we repeatedly compute syndromes of shifts of R until we get a syndrome that's a burst of length at most 3. So in this syndrome, all the non-zero entries lie in the first 3 components, which form a non-cyclic burst of length 3. We conclude that the error polynomial is x to the 6th times S9, which is this polynomial or this vector of length 15. Finally, we decode R to R minus E to get this code word. You can check that C is indeed a code word by dividing C of x by G of x and making sure that the remainder is 0. I mentioned before the notion of interleaving. Interleaving is a simple idea that increases the cyclic burst error correcting capability of a code. Let C be an NK linear code with cyclic burst error correcting capability T. Here I have S code words, and I've written out the coordinates of these S code words. Interleaving C to a depth S means the following. Instead of transmitting the code words C1 through CS in that order, we'll transmit the columns of the above array. So we first transmit the symbol C11, then C21, then CS1, then C12, C22, CS2, and so on. So instead of transmitting C1, C2, and CS, we can think of transmitting this fat word C star that's composed of the symbols of C1 through CS. Observe now that if any cyclic burst of length at most ST occurs in C star, then this results in cyclic bursts of length at most T in each of the original code words C1 through CS. For example, if the cyclic burst affects these S plus 2 coordinate positions of C star, then the code word C1 is affected in 2 positions, C12 and C13. The last code word CS is affected in 2 coordinate positions, namely CS1 and CS2, whereas the other code words are only affected in 1 coordinate position. So the original code words only suffer from cyclic bursts of length at most T, and these errors can be corrected using the error trapping decoding algorithm. To summarize, if C star is transmitted and there is a cyclic burst error of length at most ST, then we can de-interleave the received word R star to get length n vectors R1, R2 up to RS. And then the decoding algorithm for R1, R2 up to RS recovers C1, C2, and CS. I can state the following theorem about interleaving. Let C be an NK linear code over F with cyclic burst error correcting capability T. Let C star be the code obtained by interleaving C to a depth S. So C star is a set of all the fat vectors that you get by interleaving all collections of S code words to a depth S. Then C star is a linear code of length ns, dimension ks, with cyclic burst error correcting capability T times S. Furthermore, if C is cyclic with canonical generator G of x, then C star is also cyclic, and its canonical generator is G evaluated at x to the power s. I'll leave the proof of this theorem as an exercise, but let me highlight the main elements of the proof. To prove the first claim, you need to show that C star is a linear subspace, so it's closed under vector addition and scalar multiplication. You have to show that C star has length ns, which is elementary, and that it has dimension k times s, which you can see by counting the number of code words in C star and seeing that it has q to the ks. I've already justified that C star has cyclic burst error correcting capability Ts. For the second claim, you need to show that G of x to the s is a monic divisor of x to the ns minus 1 of degree ks. This isn't hard to do. And then you should show that G of x to the s divides C star of x for all code words little c star in the code C star. This would prove that every code word C star in C star is in the cyclic code generated by g of x to the s. And since C star and the cyclic code have the same dimension, they must be equal to each other. And that would prove that C star is indeed cyclic. Here's an example. Recall from slide 133 that this degree 6 polynomial g of x is the canonical generator for a 15-9 binary cyclic code with cyclic burst error correcting capability t equals 3. And so it follows from our interleaving theorem that g, evaluated at x to the 100, which is this degree 600 polynomial, is a canonical generator for a binary cyclic code of length 1500, dimension 900, with cyclic burst error correcting capability t equals 300.
We're ready now to study BCH codes, a special family of cyclic codes. We'll need quite a bit of algebra, so we'll spend the next 4 video lectures studying more properties of finite fields. In V6a, we'll see the notion of subfields and extension fields of a finite field, and we'll introduce minimal polynomials of elements of a finite field. We'll then study useful properties of these minimal polynomials. We'll see you then in V6a. Have a great day.